Can you hear me okay, everybody?
Yep, I can hear you.
Thank you.
And you couldn't hear her before, is that correct?
Correct.
Okay. All right. Okay, so we can go ahead and get started. This is being recorded, so if anybody misses anything, you know, they'll have something to refer back to. So we just want to talk a little bit about filter and fluorophore selection before we get into selecting filters in the Airy Scan or in the 980. So why use fluorescence? So we want to generate contrast in our sample. And we do have some transmitted light techniques that allow us to do that. So some phase contrast and DIC, but fluorescence gives us molecular specificity. And so we can tag a particular molecule or protein or structure with a fluorescent molecule or dye of our choosing to then differentiate two different structures from one another. And this is of course a very powerful tool that has been developed over the years. It's why Chris and I have jobs currently. But there are some caveats to really collecting our fluorescence in a very careful way. So when we talk about fluorescence and we talk about photons emitted and photons, excitation photons, we're really talking about a small portion of the electromagnetic spectrum. And so on the long end, from about 800 to 850, on the short end, about 350. So in terms of the entire electromagnetic spectrum, visible light is a very, very small portion of that. Of course, as we go from long wavelengths to short wavelengths, we see an increase in energy, and we're going to use this to our benefit. And so when we talk about generating light, so incandescence, you know, light bulbs, we all are familiar with that. So luminescence, so in this case, the example is this firefly. So in our experiments, we may harness this as luciferase, so adding an enzyme to an animal that has cells expressing luciferase, and we can see those light up in the body of the animal. So chemiluminescence, so the addition of some sort of chemical reaction to create our light. And then of course, bioluminescence, where we derive our fluorescent proteins from. And we have some fluorescent compounds down here. So generally, when we're talking about microscopy, we are looking at fluorescent proteins derived from bioluminescent organisms and fluorescent probes created in the lab or naturally occurring. So when we talk about molecular fluorescence, what is happening at the molecular level? And so we have two states of our fluorophores. We have a ground state and excited state. And so the ground state is where your fluorophores exist before we hit them with any light. And so they're just down there chilling, waiting to be excited. We excite them with a short or a wavelength that we know that they'll absorb. And so we've all looked at absorbance and emission spectra for our different fluorophores, or at least I hope we have. And so the wavelength of light that we excite them with is going to be determined by the physical properties of our fluorophores. And so our fluorophore will absorb a photon. It will go into this excited state. After a period of time in nanoseconds, it will emit a photon of lower energy and thus lower wavelength. So that will be our photon emitted. And we do have a little bit of other release of energy as well. And so the most important, I guess, property of fluorophores that we want to look at today is the excitation and absorption. And so for example, FTSE, so a very, well, not so commonly used fluorophore anymore, but we can say this is Alexa 488 in this case. So it has an absorbance spectrum and an emittance spectrum. And so FTSE is maximally excited at 488, and it maximally emits at around 525. And so that difference is what we call the Stokes shift. And so when we're looking at our microscope and we're looking at how we're exciting and how we're catching those emitted photons, we want to make sure that we're doing so maximally. So another couple little properties of fluorescence molecules that I want to point out too, in addition to the excitation and emission spectrum, are the extinction coefficient. So how well your molecules absorb photons. So, you know, the more efficiently they absorb photons, you know, hopefully the more efficiently they will emit photons. So the quantum yield is that ratio. So the ratio of photons absorbed versus emitted. And that gives us our brightness. And so it's that extinction coefficient times the quantum yield. And when you're looking at your fluorophores, you know, the product sheets and the information that either the manufacturer or, you know, if a fluorescent protein has been created, you should look at these values, and you should know, you know, based on these values in comparison to other fluorophores, how bright you expect them to be. You also want to take note of the photostability as well. So sometimes photostability is something that has to be determined empirically. We do understand the photostability of some molecules better than others. So for instance, FTSE is not very photostable at all, and which makes it a fairly terrible fluorophore. Whereas Alexa 488 has very high photostability, which makes it a much more robust fluorophore. And so when you're doing techniques like laser scanning confocal and you're really using a high concentration of light at the sample, it's really important that your fluorophore be as photostable and as robust as possible. And so this is a quick table of some fluorescent proteins in this case. So we have our excitation maximum, our emission maximum, our extinction coefficient, the quantum yields, and then the relative brightness of EGFP. And so if you look at these values, you can see, you know, they're similar. But if I were selecting a fluorescent protein just based on this chart alone, I think I would probably pick I would probably pick superfolder GFP. And the reason why is so M-wasabi does have a slightly higher relative brightness, but the excitation maximum is at 493, whereas the excitation maximum of superfold GFP is 485. And that 485 is closer to the 488 laser that we have on our system. And so we're going to be better exciting the superfolder GFP than we will the M-wasabi. So your fluorescence characteristics can also be environmentally dependent. So a common example is pH. So with FTSE, for instance, you know, the higher the pH of FTSE, the brighter it gets. And so if you are trying to image FTSE in a more acidic environment, it may appear dimmer or it may appear to be a worse fluorophore than if you are imaging it more basic. So the chemical composition of the solvents can also have an effect. The binding of the effector, so how well it binds to your protein of interest, and also too, you know, whether or not it's a calcium indicator or otherwise a voltage indicator. The charge and the concentration. So one of the things that I think is overlooked is the concentration. And so it is possible to over concentrate fluorophore in your sample. So there are situations where an overabundance of fluorophore will actually quench instead of being brighter. And so it's important when you're setting up, you know, an unknown protocol, or you're working with a brand new fluorophore that you've never worked with, to do a few titrations. And so it's never a bad idea to start with the manufacturer's recommendation, but also, you know, try slightly less or slightly more concentration of the fluorophore to see if that changes the overall result. So now when we come to imaging our fluorophores inside the microscope, let's talk about the individual components. And so traditionally, and actually we do still have some of these in the KEC, we used just white light, and that white light was then filtered with an excitation filter. And so here are some examples of those arc lamps. So here circled in green, so this is the spectra, or the light output of a metal halide lamp. And so you notice that it's not just straight across the board, so it has peaks in its emittance. And so, you know, lucky for us, the peaks are sort of located where we want to maximally excite our fluorophores. But you can see, you know, past 300 and actually even past 600, the overall emittance of these metal halide lamps really goes down. And so if you're using a lamp like this and you're trying to quantitate fluorescence intensity, you at least want to be aware that your light source is not completely flat across its spectra. To the right, we have our Xenon Arc Lamp. And so these have emittance at slightly lower wavelengths. So these used to be used very much with imaging dyes like Thera that have very, very low absorbance. But again, so not a lot of light being emitted in this visible range, a lot of light being emitted in the IR and the near IR. Down here, we have an example of an LED. So this is what I would consider a more modern light source. And so you do see that there is quite a difference in the emission of these wavelengths. So while they're a little bit more consistent than, say, the metal halide or the Xenon Arc Lamp, it's still not straight across the board. And lasers suffer, you know, similar problems as well. So when we say, oh, we're imaging at, you know, 0.5%, is that 0.5% the same in actual concentration of photons across the board? Sometimes that's calibrated, sometimes it isn't. So it's always good to be aware that the output of your light source might not be consistent. So now we've talked about excitation. So now let's talk about the different kinds of fluorescence filters and mirrors. And so traditionally, we have short pass filters, so it will allow through wavelengths below a certain threshold and block wavelengths above a certain threshold. The inverse is true for long pass filters, so it will block wavelengths of shorter wavelength than the cutoff and pass longer wavelengths. We don't see long and short pass filters very much in microscopy anymore. Generally, filter sets are what we call band pass, or sometimes you'll hear them referred to as notch filters. So the notch being the band pass that the filter allows through. And so in this range, there are wideband filters. And again, don't see these very much anymore. It's generally more these narrower band pass filters. And then I've actually never seen this third combination, the short and long paths in conjunction. Generally, everything is this narrow to medium bandpass or notch filter. And so another piece of optics that we have in the light path is this dichroic mirror. And so the dichroic mirror serves a very important purpose. So what that is going to do is it's going to reflect down the excitation light towards the sample, but it's going to allow through our emission wavelength. And allow that those emission photons to be collected, pass through the emission filter into our detector, which is generally going to be a camera nowadays. And so when we talk about matching filters and fluorophores, why do we care so much about this? So as we know, fluorophores do not have discrete, neat and tidy excitation and emission curves. They're messy. So for instance, we're looking at Alexa 488 and FITSI here. The curves are nearly identical. And so, we have our excitation here in the dotted line, our emission in the solid line, the excitation filter spec in the dark blue bar, and the emission filter spec in the dark green bar. And so you see, we're maximally exciting and we're maximally catching the emission. We are missing a little bit of our emission curve, so the shorter end and the longer end, but for the bulk of that emission spectra, we're catching it. And so when we select fluorophores, we want to bear in mind the filter sets that we have on our microscopes. And so, in our case, well, and not so much in the case of the 980. So the emission is variable in that system, but in anything that uses filters as their emission discrimination, the specs of those emission filters are set, right? And so there's not a whole lot we can do to change those. And so we want to make sure that we are very carefully selecting our fluorophores. And so when we look at spectral separation, and so you can see we have now the addition of DAPI and the addition of Alexa 568. And so what we see here is, so, DAPI is fine. We're not exciting that at all with this filter set. However, we are exciting Alexa 568 just a tiny bit. However, our emission filter is going to not allow any of those emission photons to pass through. So this is still a good filter set for this fluorophore combination. And if we add the DAPI, so we have our excitation and our emission. With this DAPI filter, we are missing a lot of the DAPI curve. However, it's not such a concern because DAPI is such a bright fluorophore. It's fairly photostable. We can really afford to sacrifice a lot of the emission photons. And another thing that you'll notice about the DAPI curve too is it really bleeds through into the rest of the visible spectrum. It would be impossible to capture all of it without suffering serious bleed through. And same with the excitation and emission for the 568 filter. We're maximally exciting it. And we are missing a little bit of that emission curve, but our excitation and emission are nicely separated. And here is everything together. So, this is a really good example. So I would say, if you had a microscope with these filter sets, one fluorophore that you probably wouldn't want to use is perhaps Psi5, or no, sorry, Psi3. So Psi3 really falls sort of in the middle of 488 and 568. So let's talk a little bit about bleed through. So this is when we detect multiple fluorophores in the same emission range. And so bleed through and the prevention of bleed through is really where the 980 is going to shine with that, that quasar detector. And so the way we visualize bleed through, so here in the instance on the left, so we have a DAPI long pass filter set. We can nicely see the nuclei, but we can also see the outline of the cell that is stained with Alexa 488. And so this bleed through, it gives us a less clean image of our nuclei. Whereas if we're using a nice short or a nice narrow band pass filter, we only see the image of our nuclei. And like I said here, so DAPI has a really long curve. And so you do have to really keep your emission filter really tight in order to not catch the emission of the other wavelengths in your experiment. So one last thing that I wanted to bring to your guys' attention, and this is something that I'm going to implement for the scopes in the KEC, is getting them loaded into FP-base. Can you see that on my screen?
Not yet.
Oh, here it is. There it is. So FP-base is a tool that was created recently that allows you to build microscope configurations, build filter configurations, and look at your fluorophore fluorescent protein spectra on top of them. And so it's a really great tool for visualizing your microscope setup before you even get started imaging. And so in this example, and it looks a little messy right now, so let me clean that up a little bit. All right, so now we have the visible wavelengths. And so I have in here an example of a microscope, and I'm using the Andor spinning disk as an example. And so we have our 4 emission wavelengths here and our 4 lasers. And so we've got a Sumrock 425 DAPI emission filter here, our 488 emission filter, our 594 emission filter, and the 630 emission filter. And so we can see these all in the spectrum. We can also overlay our laser emission or our laser excitation on top as well by selecting the different lasers. And then from here, you can select your fluorophore of choice. And so these are user added fluorophores, but I have not found something that does not exist in this list yet. So for starts, I'm going to start with DAPI. And so you can see that we have our excitation curve of our DAPI fluorophore, the emission, and our 404 laser. So you can see with the 404 laser, we're very minimally exciting DAPI, but again, it's so bright, and there's always too much of it in everybody's samples. So you can really afford to minimally excite it and get a nice signal from it. If I look at, let me look at Alexa 555, because that's one that comes up quite a bit too. Be very literal with this thing. And then I think the laser that we would think that it would be best excited is the 564. So again, so it's not terrible. But if I were choosing between Alexa 555 and Alexa 568, I think I would choose the Alexa 568. And so when we're talking about, setting up our filters properly and choosing fluorophores carefully, this is really what we're talking about. So it's just all about knowing the microscope that you're using and knowing its spectral characteristics. And again, with the 980, it's really, well, at least for the confocal, it's really the excitation wavelengths that are fixed. The emission are variable, but it's still very important to know the spectra of your fluorophore. So just because you can set the emission properties of your microscope channels to whatever you want, you really need to know what it is you want. And so, like I said before, one of the things that I plan to do in the near term is to put all of the Keck microscopes into FP-base, so that going forward, you'll be able to go through here, look at the filter sets that are on each microscope, and see how your individual fluorophores match up against the individual microscopes. Okay. Does anybody have any questions? I know that was kind of fast, but
It's easy to go on a roll, isn't it?
all right. So I guess if nobody has any questions, we will continue on with the 980. So thank you so much.
All right. Let's see. Let me share my screen here one more time. There we go. Excellent. Okay. So what we're going to do now is basically carry that conversation forward, specifically in terms of setting up the 980 as well. And we will do this for the confocal type channels that we've already worked with. We'll also introduce setting this up on the Airy Scan. And I think it's a good idea to do both of them today, even though we won't cover the Airy Scan in terms of imaging until tomorrow, just because they do represent sort of the two different types of filter arrangements and settings that Cassandra just mentioned. So the Airy Scan at the end of the day is actually a filter-based detection range that we're going to be working with. And whereas the confocal detector, the spectral detector, we have very fine control over exactly what wavelengths are reaching those detectors. And so I think it'll be a good exercise to basically try to work with and play with both of those. I'm going to back up for a second, and I'm going to keep this imaging setup region open at the moment. I think we can trim away some of this stuff here. But what I'd like to do is go back to that slide that I showed you, showing you what the scan head looks like in the LSM 980. And now maybe as we kind of keep on revisiting this, I'm hoping that it'll make more and more sense. This is on the desktop, and this is the Zeiss literature folder that I promised I would have filled with stuff. And just to show you that it's now filled with stuff. So there are a whole bunch of different images and also PDFs and movies that are going to help describe kind of how all of this stuff is working. So let's see, I am going to just start with the scan head to begin with. So this was the scan head that I showed you at the back of the microscope. And we can see that larger unit here, which is the standard scan head. And then the little shoebox on the side was the Airy Scan. And so just to kind of break down this light path, because again, it's similar to what Cassandra had shown in terms of wide field in some respects. So on the 980, you basically have a couple of different ports where laser lines are going to be coming in. So these are our excitation, or sort of the analog to the lamps that we're giving it excitation for wide field fluorescence. So number one here, and then this other white line right here. These are our two laser input lines. One is for invis type lasers like the 405, and then the other lasers are all basically piling in here. these two wheels that you see, these are the dichroics, similar to what Cassandra had shown, that basically guide the laser light to the sample and allow the emissions to pass across to the detection side of the scanner. So again, you have one of these for each of these laser lines, and they basically work like multi-band pass filters. So basically a very narrow range around the laser lines are going to get reflected to the objective, which you see over here. And then you're going to have the emission signals basically coming back in gold here. And those are going to be allowed to pass through these dichroics, except for that very narrow range around the laser lines. So we're going to scan the laser across the sample, pixel by pixel. And we're going to basically recover all of that to our photomultiplier tubes. This emission signal is going to come back through these dichroics. Everything goes through a single pinhole, which you see right here, number 5. And I know I haven't talked about this in much detail, but we will get to this more when we do Airy Scan tomorrow. Once we get through that pinhole, we basically have a choice. And this is given to us by this first filter wheel that you can see right here. So if you're only doing confocal, then you'll have this set to be a mirror so that all of your emission signals are going to be sent to this internal confocal detector here. If you want to use the Airy Scan, then we have a couple of different filter options here that are going to allow light to pass through and make it to this extra shoebox that we have on the right-hand side of the scan head. Once we get to this point, there's a second filter wheel that we can use that will, in combination with the first one, determine what wavelengths actually reach the Airy Scan detector. If we go back to the confocal side of things, whether we're using a mirror to pick off, to take all of the signal, or whether we're using a different filter to peel off some wavelengths to reach the Airy Scan, some of the light is going to end up here in these internal detectors. And so again, this is where we have a couple of fancy things here, like a spectral recycling loop and a grating. All of these basically help to recover as much emission signal as possible. But at the end of the day, for the purpose of this discussion, what these do is they basically break up the light into their component spectra. And so that entire range of the electromagnetic spectrum that Cassandra showed you, from basically 400 or so out to about 750, we can separate and we can project across these 3 different detectors that we have. And we do this in a couple of different ways. We can pick off different wavelengths with these prisms that you see right here. And these will allow us to send some wavelengths of light to these 2 side detectors, these metal alkali ones that I had mentioned earlier. And anything that these prisms don't send a different direction, we can end up having the rest of that spectrum projected across this 32-channel spectral detector that we have here. And let me see, I think I should have a talk here that shows one more thing that I would like to. This quick guide might work. Otherwise, I might have to bring back my original. No. No. All right. Forget that. But if you remember what I had shown you in the lecture, in the slides that I showed earlier, is that we can basically use these 2 side detectors. They don't care about spectra really, except for what the prisms send to them. So these 2 detectors on the side are going to eat photons. They're going to detect photons no matter what wavelengths they are. The spectral detector here has 32 different elements, 32 different detectors spread across this entire spectral range here. And so when we send light to each of these different elements, it means that we can pick up and separate those just based on the properties of the detector itself. So this is what really gives us the power to do spectral and a really fine control over exactly what wavelengths are reaching this detector. And that's the reason, just to kind of go back to the Airy Scan and circle back a bit, that we can't use this kind of spectral separation on the Airy Scan. We have to use filters instead, because if you take a look at the physical space of this scan head for the confocal detectors, we're using that space to be able to split apart different spectra with very fine control. But for the Airy Scan detector, we're using space to help us improve resolution and sensitivity. So because we can't work with spectral separation here, then we're using these regular filters to really nicely send exactly the wavelengths that we want to this, but with less control than we have in the confocal detector scan head. Does that make sense? All right. So what I'd like to do now is I'm going to bring up Zen, which you can see in the background here. And I'm going to talk about all of these different components in the imaging setup so that we can go through some of these configurations with a little bit more detail. Now, I'm set up right now on the 488 track. Again, you can see the laser, the 48 laser line here, and you can see the detection range that I want to work with here. You can see that I'm working with the channel S detector. There's another channel S2 here. And then we see channel 1 and channel 2 as well. This channel A is the Airy Scan detector. So I can actually use that in confocal mode should I choose to as well. Channel 1 and channel 2, again, are these two different side detectors here that you see. And channel S, because we have a detector a compound detector that basically has 32 different channels, I can actually break this into a couple of different regions across the detector as well. So I can actually use this little plus and minus button here. I can expand our channel S detector to include up to 8 different regions in addition to the 2 side detectors that I have. So a total of 10 channels basically simultaneously, plus the Airy Scan actually. So you can really work with a lot of different detectors at the same time. Now, you don't really want to do this because most of the time you're going to be encountering overlap if you try to use so many at the same time. But we can use this to make the system very flexible when we need to. So let's go back to the kind of setting that I had here before. For these different ranges, what I can do if I want to adjust this is I can just grab this bar here and I can slide this range however I want. And I can either do that by working with this element here on its own, or I can do this by typing in to these values here. So if you like round numbers, you can basically type in the values exactly as you would like them to be. So pretty flexible in terms of being able to set all of these things up. What I'm doing when I'm making these adjustments and dragging these is I'm basically adjusting the position of these stops and the hard stops and the prisms that you have here, so that I'm tuning just that range and working with that on the detector. And if I wanted to add a second channel at the same time, then you can see all I need to do is basically check the box, and I could click on this die region, and you see a very similar list to the one that Cassandra had shown as well. This is basically the same one that you can pull off the internet on a number of different Spectra viewers. And in this case, let's say that I want to do something like Alexa 568. So I can just type that in here, double click, and I've just added that to this region as well. So I could, if I wanted to, collect signal from both of these at the same time, but exactly as was just discussed, this isn't usually a good idea, because if this laser line, even though it's much narrower than the emission filters that you were shown earlier, even though this strict excitation here is very select wavelength, if we cross excite, or if this green signal extends into this red range, and if we're not careful enough to avoid that region of overlap, then we're going to run ourselves into trouble, and we are going to see crosstalk. So very often, if you see this much overlap here, you would choose to move it to a separate track and do it independently. This is helpful though. having the ability to check a couple of these, even if I'm not going to use it here, this is really helpful to work with because it allows me to set this range in an intelligent way. So I can look at where my laser line is. I can set this up so that I'm capturing the peak of my emission for 488 in this case. And I can use this emission cartoon to make sure that I'm not actually encroaching on the range where my red fluorophore is occupying spectrally. So I can avoid crosstalk just by looking at these two different curves and making sure that I tune this properly. And you can see that for 488, this is pretty easy along with 568, because again, it's a really good pair to work with. But just to go back to some of the examples that you've seen earlier today, if I do 555 instead, you can see that I have to be a little bit more careful, and I maybe have to pare back here a little bit. As I'm doing this, I'm making sure that I'm selective in terms of the signal that I'm going to get, that I only want the 488. However, I am losing light, I'm losing photons every time I claw back here a little bit. And especially if you have to do something like this one where you're very off peak at this point, you really are going to lose a lot of signal, and you're going to struggle with your confocal as a result, needing higher laser powers, higher gains, and things like that. All right. Another consideration, even if we're working with the, in situations where maybe you end up with overlap, maybe you didn't realize, or maybe you just need to squeeze out that much light, sometimes you can get away with this. But if your green signal is very weak, and if your red signal is very strong, then to collect the green here, you might end up using higher laser powers, you might end up using higher gains. And as a result, you will more easily pick off some of this red signal that you don't want if you're not careful. So again, in situations where green is very weak, red is very strong, this might be a problem. So you need to be extra careful in those cases. All right. So let me go back to this one because my floor actually is 568. So I'm going to use this one more time just to be able to set this range neatly here so that I'm not really getting the red signal. And once I've done that, I can just turn this off because I'm really not doing any imaging on this one at the same time. So let's go back here. All right. So this would be a fairly clean configuration this way. Let me activate the other channel here and we can take a look at this and see how this one looks. So just like before, one of the things that I can do, and you can see the footprint of me doing this here, is I can add in this cartoon of the Alexa 488 here for a minute to help me inform myself where I want to set these values for the other tracks as well. And so I had moved these around a little bit. I'm pretty sure that I had this a little bit further over here because we really don't have the green channel. And I'm not too worried about the DAPI out this far. But you'll see that let's actually do this. So if I keep this right down to here, I think we might even see some DAPI in this channel. So we'll try that out. But you can see that I can make sure that the DAPI is basically moved away from the green as much as possible. Again, this is really just in case this 405 ends up cross-exciting the green. You would end up seeing that green signal if your detection range here was broad enough. All right. And again, as Cassandra mentioned, we're losing a lot of light from our DAPI emission, but it's so bright anyway that it usually doesn't make a difference. If you are struggling with the signal, though, one of the things that you might want to do is to try to expand this range a little bit. And again, then you need to be very careful with your crosstalk. Let's try this out. Let's see what we get. So I have a different sample on here, cells that are labeled with 3 different channels. And so I hope it's still in focus after we've talked all this time. Here you can see nice microtubules in green. And you can see I'm doing a decent job with the range here. Let me switch over to the other track and let's see what these look like here. So here's my DAPI. You can see pretty nice already. I didn't even have to really adjust it yet. I could fill a little more of the dynamic range if I wanted to, but I really don't need to. But I wanted to because here's what you can see, a little bit of signal out here. So this could either be background from the cell, or it could be my red signal coming in. We're going to know as soon as we take a look at the red. Definitely not the red. So here's my red. And this is a great example of crosstalk and where DAPI can run you into trouble, right? You can see here this beautiful actin staining in the background. And you can see that as I boost this signal, we're going to get more of that actin looking pretty nice. But in the background, you do see these nuclei here as well, okay? And let me just back off on the signal so that you can see it a little bit better. So here's my nuclei showing up in my red channel, clearly crosstalk. This is a problem. And I can tell that it's my DAPI, number one, because if I turn off this 405 laser, you basically lose that signal. Okay, so this tells me that as much as I wanted to try to speed things up here and collect both of these signals at once, I can't because I'm running the risk of introducing this kind of bleed through into my image. And so I have two choices basically now. One thing that I can do is I can try to move away from my DAPI channel in terms of detection range. So I can try to slide this over. I'm losing a lot of red, but hopefully I can get a clean signal without DAPI. And let's try that and see if it's the case. So DAPI channel is here. Here is my red. You can see that I have a lot less signal to work with. I'm still getting these nuclei in here. So this isn't going to work. And even if it did, you can see that my image is getting grainy and I'm having to ramp up my gain and I'm having to ramp up my laser powers just to be able to try to get that red signal working. So let's try to do this then another way. I'm going to go back to what I had here. I'm going to be happier with this anyway because I get to collect all of this signal, and I am going to duplicate this track by working with this little option gear here. And this track is going to be my 561, and I don't have 561 here anymore. I will. For this track, I'm going to turn off the DAPI channel. I'm going to turn off the 405 laser. And I'm just going to do red. And likewise with the blue here, I'm going to turn off my 568 channel. I'm going to turn off my 561 laser. And I'm just going to do blue in this case. All right. And here, well, we'll try it first, but I can even see if I can expand this range a little bit, and we'll see whether or not we get any green creeping in also. So if I go to live, my DAPI always looked good, but it should look fine here as well. My red now, you can see doesn't have that nuclear element to it anymore. And so this is where this configuration really comes out ahead. It doesn't save me time, unfortunately. I have to do another scan, but it's really clean. And so that's honestly the most important thing most of the time. So I'm pretty happy with that. And like I said, let's go back here. Let's see if we can actually expand this range out a little bit. And I know there we go, good. I know I'm running a risk here because my green is in the range that I'm detecting here also. So I could run into problems with that. And we're about to find out as soon as I hit live. Not bad. A little bit maybe. And yeah, and I think, if we boost the signal up a bit, yeah, I think we're getting a little bit in there. And so let's keep it like this, and let's take just a quick snap of everything, and let's see, what looks like it co-localizes or not. All right, and again, we're just doing a very fast scan, but at least it allows us to kind of see what these are going to look like. So here, if I turn off the green and turn off the red, yeah, I think there's a little bit of crosstalk with this. The red, though, looks nice and clean, actually, for both of these. So it looks like we've got nice separation here between these different channels. But otherwise, I think for the blue, we would want to narrow this range a little bit. Does that make sense in terms of what we're doing here? All right. Now, one of the other things that I did here, just to let you know, is as I was playing around with these different settings, I switched us from frame fast to line as I did this, or sorry, to frame. And so it's worth quickly mentioning what frame and line mean in terms of how flexible we can be with our configurations here. So at the moment, I have basically DAPI on the first track, 488 on the second track, 568 on the third track, totally separate. The laser for each, the detection range for each. So really just one channel at a time, almost like doing wide field fluorescence. When we're scanning, in frame mode, what we're doing is we're basically collecting the entire 2D frame in DAPI, and then we're going back and doing the entire frame in green, and then we're going back and doing the entire 2D frame in red. And what happens with this is it's a little bit slower than the line technique that we could use, and I'll talk about that in a second. But what it allows us to do is during the time that the laser, that the galvos are flying back to the original position to start the next scan, it gives us a time, it gives us a pause where we can actually change hardware in between each one of these tracks. And so if I wanted to extend this range for my DAPI, even though it's overlapping with where the filters would be in the next track for 488, I can do this when I'm in frame mode. So this gives you really full flexibility over the detection settings and how they're working. Now, if I switch to line, you'll see that first of all, it'll warn me that several track settings will be overwritten and that they'll be applied to all of these tracks. And so everything from the DAPI track just got transferred over to these other ones. And what I want to show you is when I'm doing it like this, I'm basically just doing a line of blue, a line of green, a line of red, and then moving down and do the next line. So this is going to be faster in the long run because we don't have to wait for the laser to fly back between every track, but it's so fast that we don't have time to change any hardware in between. And so that means pretty much everything. That means I can't change these beam splitters. I can't change my pinhole. I can't change these filter settings. And I can't change these prisms and blocks that are basically directing traffic to each of these different detectors. And so because of that, if I decided that I wanted to make a change here and extend my DAPI into this range, if I take a look at the other channel, well, assuming it lets me do it, if I take a look at this other channel, you'll see that it would encroach on this. So let me do it here with the green instead. So if I do this with the green, you can see I can get the entire range, but now I'm basically encroaching on my red range. And if I dial this back again, you can see that I'm just playing tug of war between these two different tracks. So line is fast, but it doesn't give you as much flexibility in terms of setting these different detector ranges.
I have a question.
Yep.
What's the difference, if there is any, between the switch track every frame or when you're doing the setup at the beginning, if you just set every channel to be, each color to be on a separate channel? Would that end up being the same?
Sorry, can you ask that again?
Yeah. If you change the settings to switch track every frame, would that end up being the same as if from the beginning you had just separated all three of your colors?
Yeah.
Yeah.
Yeah. If we go back to frame now, we can do anything that we want. So if I start it, like if I start a configuration in line then each one of these tracks is going to exactly match in terms of the different hardware settings. So if I start from this, and then if I switch to frame, then I can go back and make changes. And for example, I could have this one extend its range without affecting the other tracks. Does that make sense? Does that answer the question?
Is like when you do smart setup,
Yes.
and it lets you choose between like combining two tracks, two colors onto one track, or separating them out onto individual ones.
Right. Yep.
Is that the same? So like say you picked the fastest and they're like next to each other.
Mm-hmm. Yep.
And then you switch track to every frame. Is it going to essentially look like the best signal anyway? Because you're switching every time.
So things like smart setup, smart setup is basically going to give you either line or frame depending on which one of these you choose. So
it is kind of like the two different ways to end up picking that.
yeah. So you could end up picking them here, but you don't get a choice. You don't get control over it. But I can tell you that because this blue range here is optimized to collect as much DAPI signal as possible, this would have to be a frame switching configuration that smart setup would give you. Whereas these ones here, it looks like it would be keeping it in line because you've got these ranges that are basically not overlapping as a result. So smart setup will try to give you line when it can, but if you want a configuration here that's going to maximize signal collection, then it would have to resort to a frame switch.
Right. Okay, thank you.
Yeah, no problem. All right, so that's pretty much everything here. I guess one other thing to mention, since I haven't really touched on it yet, is kind of tucked away at the bottom here, we have this TPMT. So completely different than the topic of spectra, but if I want to do a bright field track, I can just check this box. It gives me a new channel here, and I can get a bright field image at the same time as I'm collecting my other channel. So this is kind of nice in terms of bright field. What it does is it effectively, and this sample is going to be boring because there's really no signal on it, or it's very thin cells, so there's not really much going on with it. But this basically would give me a bright field image for free. It doesn't take any longer. It doesn't use any more laser. I don't have to bleach anything. I'm just piggybacking off of an existing channel to get this bright field image, which again, obviously I should have kept the conval area on there. It'd be a lot more exciting. Let me work on that a little bit. But anyway, so this is how we're working with the regular confocal, is with this kind of setup right here. So does that make sense to everybody? Do we want to try an exercise where we work with some of your favorite floors and you kind of guide me what to do? Silence is going to mean yes in this case. So let's pick a few different floors, because this combination, as we've said, is pretty easy, right? So what else do people work with here? And maybe I'll start with smart setup actually to begin with. So name your favorite floor for.
We use 488, 546, 647.
Okay. All right, here we go. So you can see again, the best signal, it's going to just give you 4 different tracks. So this is going to take twice as long as trying to do the fastest way. Fastest would combine the blue and the orange at the same time, the green and the far red at the same time, because these have the minimal overlap between all of these. And maybe the smartest thing is to do the DAPI with the far red, because it generally doesn't emit out that far, and separates your green and separates your orange, which otherwise would have considerable overlap with any of these other channels if we were doing them on the same track. So smartest, I think in this case, saves you one scan at least, so it's a little bit faster. And let's take a look at this and see what it looks like here. Well then, Smart Setup doesn't like it. That's interesting. Okay, I will set it up from scratch. So if we want to here, we can just go in and add a confocal track. So this is how you would build it from the very beginning, should you have to. And I'm going to emulate what I think that that was going to do, basically. I'm going to add a couple of other elements here that we didn't really get a chance to talk about earlier as well. So let me bring this up a little bit. Let me show everything. And showing everything on this allows me to see my lasers. It allows me to see these dichroics here. And those are the dichroics that we were looking at, these two filter reels that are number 2 right there. Now, the reason why I'm doing this is because I want to make sure just for each one of these that I have 405 listed, because I'm going to want to use my 405 for one of these tracks. And I want to make sure that I have the 488, the 561, and the 639 that I'm going to be using for these other sources as well. All right. Let me ask you a question for your 546. What, if you're using these on confocal, what laser do you typically use to excite them?
Well, before I was using the 710 and we never changed the lasers. We just had a certain one set up and we told you to change it unless you need to. So I couldn't remember to tell you.
Got it. That's okay. I'm going to do one thing if I'm online here, which is just to jump out, and I haven't used FP base much, but I'm just going to go to Thermo Spectra Viewer, which is going to be very similar. And I just want to see your Alexa 546 here. The reason why I'm doing this is because the cartoon in Zen, as good as it is, it only shows the emission curve, so it doesn't show the excitation. So I'd like to go in here and show Alexa 546. And the reason why I want to look at this is because you do have a couple of different laser options on the 980. So you might be able to get away with a better excitation should it happen to work better. Although looking at this, I do not think that's going to be the case. We can choose a custom laser. We can tell it that we want to look at 561. And that would be right there. So that's actually perfect for your 546. You know, we're going to lose a little bit of the peak here because we're going to have to keep our detection range to the right of it, but it's still going to be awesome excitation. So it's ideally suited for this wavelength. That's perfect. You can see we do also have an option for a 514, but you can see that that's pretty off peak, and the relative amount of signal you're going to get is much weaker as a result. Okay, so it's definitely worth checking anyway. If we're going to do DAPI and the 555 at the same time, I'm going to split my channel S into 2 different detection ranges. And I'm going to use the first one for green, and then I'm going to use the longer wavelength one for red. And so you can see that that ends up populating up here. I'm just going to drag that over. I'm kind of doing this blind at the moment, so I'm going to pick my different fluorophores. Again, let's go for DAPI in this case. And let's show our red as well. All right. So once again, you know, we're going to activate our 561 laser, which is here. We're going to activate our 405 laser, which is here. So you can see those 2 laser lines now in the cartoon. And I pretty much guarantee that we're going to end up getting bleed through from the DAPI into this, especially if we did for 568, we're definitely going to do it here as well. So in the end, I'm going to separate these 2, but it was worth checking it out and seeing what this would look like. Let's then duplicate this track. For this one, I only want it to go as far as, let's say, 480 or 490 or so. For this part, I can increase this range and get it out of that area too if I wanted to. But we can actually overlap, we can straddle the laser here and you're never going to see that signal come back to the detection side. These dichroics are so good, and they're off angle a little bit, so you never end up getting laser reflection back to the detector. So don't worry about seeing this kind of overlap a little bit in situations where it does. Again, let's make sure that we have everything showing up here. Perfect. Okay. The reason why I'm setting this up, even though I'm only using 561 and 405, I'm not using 488 and 639 yet. I just want to try to keep these from moving as much as possible for the life of your confocal, basically, to try to keep it alive as long as we can. So if I can keep these filters in place, they're going to block just a tiny bit of signal, but it'll really help the longevity of your microscope. So now that I've got this one built, I'm going to duplicate it once more. And for this one, I'm going to keep that, and I'm going to duplicate it one more time. All right, so if you remember the way the smart setup was trying to go, it wanted to use, oh, that's using channel 2, oops. All right, so if you remember the way that the smart setup was trying to work with this, it wanted to do DAPI and far red at the same time. So we're going to change this here to 647. And you can see that range right here. I'm going to turn off the 561. I'm going to turn on the 639. And I'm going to change that too. Every time you pick a different floor, it changes the MBSs, so you have to be careful. It's trying to maximize things for you, but in this case, we know what we're doing. I can change the color of it just for the sake of color. But this looks like a much better pair, right? So we can get away with doing both of these. We're certainly not going to see crosstalk between these two. All right. So this is going to be my 405, 639 track. The next track here, and I'm actually going to switch this to line. So I'm going to make this do the same thing for each one of these. Now, when I go to track 2, in this case, I want to use my spectral detector. We can turn that off. That doesn't need to be there. And I'm going to add, in this case, let's add our 488 first. So again, I can just add 488. Here it is. I had this range set nicely so that I avoid that crosstalk, but we don't really need DAPI on this track anyway. We're getting it on the first track, so I'm just going to turn that off. It was good to see for a moment. And here I can bring this range down again to make sure that I avoid my 546. So if this is going to be my 488 track, these are the wrong lasers. I want to make sure I have this one. We're going to call this 488. We're pretty close. And I do just want to trim this range a little bit to make sure that I'm not getting any of that 546 signal. So for your combination of floors, I think that this track and this filter range is going to be the one where you need to be most careful to not extend this green range too much. So again, hopefully your signal for the 48 is bright. It usually is. Very good quantum efficiency, very good range. And I can set this range right now. I don't really need to, but I might as well since I'm here anyway. And I can set it so that when I'm looking at my 561 excitation, I've got this kind of nicely to the right of that. Let's say maybe like 565 or so. And 605 is a good place to stop. We could go out a bit further, but that's fine. All right. Okay, so I didn't need to do that here because we're not actually doing both of these dyes at the same time. That would be crosstalk madness. But I did just want to set it up because I am doing a line configuration. So that just made it easier for me to go to this track and to know that this range is already set up exactly the way that I want it for Alexa 546. So again, I had picked the wrong detector here in the first place. That was my bad. That's the one that we're reserving for 647. And again, I don't need DAPI here because I got it on the first track. So this is basically my 561 or my 546. And I need to turn off this laser too. All right, so we have the right lasers for everything. We have the right range for everything. It moved this on me, again, because we're in a line switch, so let's bring that back. Everything looks good. Does that make sense?
Yes, and I hope you save this when you're done.
Just gonna say, do you want me to save this for you?
Love that.
Okay. What would you like me to call it? Because I'm not gonna call it Zeiss.
Yeah, call it like Graybill, Grabiel.
Sorry, say that one more time.
Yeah, Graybiel.
Yeah.
Biel.
E-I-E-L.
Like baby.
Okay, got it.
Yeah, E-L. B-I-E-L.
E.
EIL?
Hang on, I'll put it in the chat.
Yeah, that's easier. I'm
Yeah,
sorry.
just put it in the chat.
It's breaking up a little bit, the sound, so. Oh, okay, got it. Perfect. So this is going to be confocal. This is going to be 405 with your 639. And then on a separate track, we're going to do 488. And then on a separate track, we're going to do 561. And this is a 3-track line. Make sense?
Looks great.
All yours. See how good it is if you actually come forward with your fluorophores and you want to do this with us here. If anyone else has floors, again, you know, I'm happy to basically work with these and to kind of build them into a setup here. This is one of the huge benefits of getting to do this with a group like this. Even though you're remote, we can at least walk through this process and kind of, I think every one of these that we do, you know, it helps maybe make a little bit more sense in terms of how we're setting this up and how we're working with it. I'm going to set my pinhole. Again, one of the things with line switching is you don't get to adjust your pinhole between these different tracks either. So I'm going to set it based on the 561, based on kind of your middle of the road, your red. And so what that means is that our pinhole is going to be optimized for this wavelength. That means that for the 488, it's going to be a little bit more open than it needs to be. So we're going to be getting a little bit more light than would be optimal at 1 Airy unit. But we get more signal, we get a little bit of a loss in resolution as a result. And then for the DAPI, even larger, but again, usually it's just nuclei, we normally don't care. For the 647, it's going to be a slightly smaller pinhole than would be optimal. And so we're going to lose a little bit of signal from this, but the resolution will be great. So I guess maybe we should have a conversation about pinhole as well, shouldn't we? I've been planning, so the reason why I've been dodging it is because I usually do this as part of the lead into Airy Scan, but I usually don't do Airy Scan and confocal on 2 completely different days. So let me at least bring it up and we'll talk about it so that you understand kind of, you know, why I'm making these choices and what that all means. So let me load up here, and I should copy this file over as well because I don't think that I have it there for you. All right, let's see. Okay, so very similar to the wide field fluorescence layout that you saw earlier, the confocal effectively is laid out exactly the same way. This is your laser, your light source. You basically end up, it's already a very select wavelength, so we don't need to worry about an excitation filter to trim that down. So we go basically straight to the dichroic, and this guides our excitation light down to the sample. Sample fluoresces, fluorescent signal comes back, is able to pass across the dichroic, and it either goes through filters or it goes through our prism set to be able to reach the detector. And on the way, you end up running into the pinhole, which is in the same conjugate image plane as your sample is. And as a result, light that is in focus is able to pass through that pinhole when it's closed down to a certain degree. And light that's out of focus is going to end up crashing against the pinhole and effectively be rejected from reaching the photomultiplier tube. Okay, so except for the fact that we're using high-powered lasers and expensive sensitive PMTs, it's pretty much the same thing that we're doing with regular fluorescence. The heart of this is the pinhole. None of this works without the pinhole. This is the whole point. And because we're only doing 1 pixel at a time, and we're not collecting a lot of light, this is why we need these fancy lasers and we need these very sensitive photomultiplier tubes as well. But really the heart of it is this pinhole right here. Now, this kind of ray diagram is what you're going to see all the time for talking about confocal and talking about the hardware and the layout. But I really find that it works a lot better to think about something like your PSF and what that looks like in terms of discussing the pinhole. And as we get to Airy Scan, it makes for a better discussion as well. And so if you think of a fluorescent point source, let's call it a sub-resolution bead or a single fluorophore molecule, you never actually get to see that object through the microscope. And partly that's because light is a wave, partly that's because optics suck. But at the end of the day, you end up getting a convolved image that's going to look more like this. So you have a bright central peak, you have these concentric rings, which are the extra orders of light around this. And this is known as your Airy Disk. When you take a look at this from the side, when you take a look at this in Z, the pattern is a little bit more complicated as well. Our Z resolution isn't as good. This is the evidence of that. And so you end up seeing a little bit more of an elliptical profile for the bead, a little bit smeared in Z, as it were. And you end up seeing that these extra orders take on a little bit more of a complicated type of pattern as well. So when you are looking at something that's in focus, and this purple line is basically representing where we are in focus, you can see that this is the pattern that we get, that nice crisp Airy disk. And as we move through focus, or as the sample moves out of focus, let's say, you see that the light shifts to these outer orders. And depending on where you are in this pattern, you pretty much get nothing in the central spot here. So this is sort of an out of focus object compared to the in focus object that we saw here. All right. Now, when we set our Airy unit, when we set our pinhole to 1 Airy unit, we're basically setting it to the diameter of this first minima, this first dark ring that you see here. And what that means is that what we're doing is we're basically including most of the in-focus light. We're only excluding these extra rings. And we're mostly excluding this out-of-focus light. And that's confocal right there. And that's also the definition of the Airy unit that we're working with. Now, for different wavelengths, the shorter wavelengths would have a tighter pattern, so the diameter would be a little bit smaller. Longer wavelengths are going to have a pattern that's a bit more spread out, a little bit larger, and so the pinhole would technically be in a slightly different spot for those. All right, and the reason why we do this is normally this would be an animation if we had PowerPoint on here and you would watch these little gray bars kind of slide to the first minima. But let me just say that, you know, what we're doing effectively is we're closing the pinhole down to this first minima, again, throwing out a little bit of light, but keeping most of it. And so this is usually considered a good compromise between signal retention and optical sectioning. You can, of course, open this up a little bit more and you'll collect a little bit more of your in-focus light, but mostly what you're going to do is collect a little bit more of your out-of-focus light. You can close this down a little bit as well. And you do see an improvement in resolution as a result. And for the first little bit, it's not that bad. Like as you get down to an Airy unit of, let's say, 0.9, 0.8, you're really just kind of clipping off the tails of these peaks. But as you encroach further and further, especially once you get past this full width half maximum here, the 50% point in terms of intensity, you really start to cut out your signal. And so if you're going to tune your pinhole, if you're going to work with it either by opening it up or closing it down a little bit, those are effectively the consequences. And so as you do that, you have to ask yourself, how important is this channel to me? Do I mind opening it up a little bit? Or is it the one that I want to resolve the best? And on the other side, you have to ask yourself, how much signal do I have? Can I close the pinhole down and still get enough signal to work with to push a little bit of resolution further? And so that basically is the foundation for what I'm talking about here in terms of setting one Airy unit, in this case to the 546. So again, with line switching, the pinhole stays in one spot. This really doesn't impact your imaging much at all because our optical slice here is half a micron, it's 500 nanometers, and our resolution in Z is really only about 750 or so, or longer, depending on the wavelength. So it's not like we're seeing much difference if we're doing a 0.5 micron section for one and a 0.5 micron section for another one, and never mind, then a 0.5 section for that one. So no big deal, right? The point is, if I'm setting this to one Airy unit, and when I click on this to be blue, that means it's going to keep this one fixed as my one Airy unit choice. I'm going to have a little bit more signal from this one because this wavelength is shorter. So I'm going to lose a little bit of resolution as a result, but I get more signal, so maybe that's good. Here with the 647, I'm closing that pinhole down quite a bit as well. And so in this case, I have to ask myself, do I have enough signal to make that work? And usually these far red dyes are very well excited by the 639. They have decent quantum efficiencies, very bright. So it's usually a non-issue to be able to do this. And for DAPI, this is the one that is going to take the biggest hit on resolution. But again, if it's really just there to show you where your cells are and label your nuclei, this doesn't matter so much. Does that make sense? Is that how you would describe it? I'm always curious.
Yeah.
Okay, good. Because I know a lot of people really just like to do it this way, and I just can't think of it that way. Where this helps a bit as well is basically when we get to talking about Airy Scan. Oh, well, here's the pictures that I wanted. When we get to talking about Airy Scan, we're basically projecting that pattern onto the detector. So we'll get back to this tomorrow, but this is how we can improve resolution and sensitivity because of this. All right. So again, you know, the purpose of this afternoon, I guess, to some extent, is to kind of walk through a couple of different examples for fluorophores and to talk about different ways to configure those and set them up. And I think it's most helpful and most relevant if we do these with yours. So if somebody else has something that you would like to throw at me, we can talk about how you would build it. If not, then what I'll do is I'll switch gears and I'll show you what the Airy Scan configuration would look like, because as a filter-based thing, it's a little bit different. And I can do that using this same example if we want to do it that way.
Good to me.
Okay.
But
Nobody else? This is kind of your going once, going twice opportunity to have me build a configuration for you. Your own resident life specialist here to
It's
build.
okay. You can just build everything for me.
I guess
No.
so. That's fine. Fine. Well, also, you know, you'll be the one who has the example for everybody else. So they might end up building off of your configuration. And so if I'm not here, you get to be the person to kind of walk through that. Is that all right?
Okay.
All right. Okay, so let's go back to the Airy Scan then. And just to show you that light path once more really quickly is that, you know, if we're sending everything to the Airy Scan, then we are basically letting all of our emission come back through. It's worth mentioning as we're talking about the Airy Scan that the pinhole in this case is going to be wide open because that conjugate image plane, that's the same for the pinhole, and your specimen focus is a conjugate image plane that's shared by the Airy Scan as well. And so effectively the Airy Scan is your pinhole. It's just a pinhole with 32 different detectors that are all 0.2 Airy units in diameter. And so pinhole is wide open. we cross one filter wheel and a second filter wheel to get there. So this is the first decision point. This is the first choice that you make, what wavelengths you want to send to the Airy Scan. And then we can trim these down even further using the second detector element. So it's the combination of these two that's going to dictate what wavelengths reach the Airy Scan detector. Now, again, while we're looking at the rainbow and the pattern here, just to point out that, you know, for confocal and for spectral, we're able to set this up by splitting the rainbow and basically sending it to different places. So we're using space to capture different wavelengths. For the Airy Scan, we're using space to capture that PSF instead. And so we don't have the luxury of breaking things up into Spectre as well, because we don't have 6-dimensional space to do that in. I wish we did. So for the moment, we're using these two different detectors to be able to decide what makes it to that detector. So if I go back here, and if I load up an Airy Scan configuration, and I'll basically start with this. Actually, maybe I'll go to Smart Setup. It's worth mentioning that the multiplex and the SR mode, both of these, basically the hardware configuration is exactly the same for each one of these. So let's go to Smart Setup, and I'm going to do the LSM thing here, and I'm going to do Airy Scan instead. Okay. And you'll notice that I really don't have a choice, right? I have to do everything as a separate track because I can't separate these spectrally. So when you're working with Airy Scan, you have to do one color at a time because otherwise you are guaranteed to get crosstalk, basically. The two different options that we have here, it's really just slight differences in filter combinations. You'll see what those look like in a minute. I'm going to try going for the smartest one here, and we'll see how that goes. It's worth mentioning that in Smart Setup for Airy Scan, we're kind of taking a bit on what we're going to do tomorrow, but you have a choice here. When you think about balancing and biasing towards either better sensitivity, better speed, or better resolution, you have basically this little decision helper here that will decide basically which mode you end up working with should you choose to. So I'm going to select for resolution. We're just going to do basic super res here, and I'll click OK. And let's see if this is going to work without kicking out an error here. There we go. All right, good. This is a great example. So here we have, Zen always starts you with the longest wavelengths first. I like to go the other way. I can leave it however you prefer.
I like to go long short.
Do you? Okay, all right,
Yeah.
then I'll do it that way. It's gonna break my heart.
Well, because Daffy excites everything.
It
and
does.
reaches everything, and
It does, I know.
the other way around is not.
It
That's
does.
not the case, yeah.
I know. For I guess my rationale was always that for a snap that matters, but for like a Z stack, you're cycling anyway. And so
That's true.
yeah. Anyway, this is all personal preference, this part that we're talking about here. So regardless, here is what this configuration looks like. And you'll notice that, you know, we have kind of a slider here. And it is worth mentioning, I'm just going to save this right now as your Airy SR configuration. And so we'll have each of our 4 different wavelengths is going to be on a separate track, and we got 4 tracks and we got line. So let's just leave it like that. Now, the reason why I wanted to do this, I want to just go back to that first one that we had for a second. And it's going to actually look just like what I left it. Oh, no, it's not good. So what I wanted to show you was these little slider bars that we have here. Those don't exist for the Airy Scan. So you don't get to see this part of the hardware cartoon. But I never mentioned sneakily that underneath this, you actually have 2 other rows here as well, these little dark gray rows. One of them is for the mirror, and this is actually our first pass here. And if I change this, you'll see that it actually uncovers this other one that you have here as well. Well, it should anyway. So this is that first gate that we were talking about earlier. All right. Now, if I go back to the Airy Scan configuration and show you what that looks like, here you can see we no longer have those sliders anymore, but we do have basically our choice of a first, the same first filter wheel. So we have a mirror, we have a plate, which is just a glass plate, which would let everything through. And then we have different kinds of short pass and long pass filters, similar to what Cassandra talked about earlier. So short pass 505, long pass 525, long pass 570, so on and so on and so on. All right. So this is where we make this first decision. And it's pretty open, right? It's basically anything shorter than this or anything longer than this. So pretty coarse at this point. The second filter is the one that you see down here. And so this one is left at a plate at the moment, but you can see that there's all kinds of different multipass options here. And so these are all listed, the spectral ranges that they allow to pass are shown in light gray. And you can see that it shows you in text beside it as well, that we have a band pass, 420 to 480, that's this range right here. This would be for DAPI. And then we have a band pass 495 to 550. So this would be for 488 right here, okay? And there's a whole bunch of different combinations here, pretty much everyone that we could pack on the filter wheel, that's for sure. And so you have different combinations of these that we can work with. So I'm going to show you the line config first, and then I'll show you, you know, how I might clean it up if we need to worry about bleed through. All right. And again, for the Airy Scan, everything on the excitation side is exactly the same. So these dichroics, we work with those the same way that we would in terms of making sure that they're appropriate for the lasers that we want to work with across this entire thing. And again, I'm doing line switching here. And with Airy Scan as well, this means that I cannot change configuration. So without having it affect all of the other tracks. And so as a result, you'll see that every track that we look at, aside from flashing a different laser, we have exactly the same emission range. And we have no change in any of the hardware components effectively. Now, as someone who's been doing spectral imaging since the LSM 510 and really being careful about choosing different fluorophores and watching out for overlap, this freaked me out the first time I ever set this up. But I have to say, it's worth trying, and it works way more often than I ever thought that it might. And here's what I mean. If we start with the far red, there's usually no problem here, right? We're far enough out that we don't have any other floors that we might accidentally excite. So we're usually pretty safe with this one. In this case, we have the 639 laser, and we have a detection range that is wide open. That's what this red area under here is showing. So you can see if I change this range, that it'll actually cut into the signal, and the red line that you see underneath here represents the ranges that you're collecting. And I'm just seeing, you know, what the emission peak for 647 would look like to help me out. But this range I'm collecting and this range I'm collecting here. So let's go back to the plate that we had. Same thing goes for the red. So for your 546, we're using that 561 laser to excite, but again, our detection range is wide open. We're collecting absolutely everything. Same thing goes for green, wide open. This range is what we're collecting, all the way from below 400 all the way up to almost 750, up to 700 and some. And same thing goes for DAPI as well. We're collecting everything here. So even though these emission signals overlap, right? This DAPI curve here clearly encroaches on the green and even onto the red to some extent. That's not an issue, actually, with this kind of line switch configuration for Airy Scan. The killer in this case comes in if you have excitation overlap, which is important to think about as much as emission overlap is. So if we have excitation overlap, which means if this 561 laser excites anything else, if it excites your far red, for example, then you're guaranteed to collect this because you have no protection on the emission side of this hardware setup. If this 488 laser happens to excite your 546 a little bit, then you're guaranteed to collect that signal. And if the DAPI, if the 405 excites anything else, then you run the risk of capturing that signal here as well. So I think, again, the DAPI looked pretty clean in terms of excitation when we were working, even with the 488 in this last sample that we had. The laser wasn't killing us. It was the fact that we tried to do red and blue at the same time, and having the 405 active was giving us an emission signal that crept into the red channel. Here, we're just collecting everything one by one. So the only problem comes in when your 488 signal excites, or your laser of choice excites more than one fluorophore. And if we go back to the spectra viewer that I hope I kept up, we can see, for example, if we type in here 488, I can see that I do really expect a little bit of excitation off of this 488 laser. And so this combination is likely going to be very, like the combination of 4 floors that you're working with here is likely going to be not a very good choice for trying to do a line switch with Airy Scan. Does that make sense? So I'm going to leave it here anyway. I encourage you to try it out and very likely see Crosstalk, and then we'll move on and I'll do a frame switch configuration for you instead. So for a frame switching one, that's where I'm going to get a little bit more creative with these different plates that we have. This one is very easy because everything is just wide open. This is very fast in terms of an Airy Scan configuration because nothing has to change. We're just turning on and off different lasers for it, which is very nice. But if I want to be a little bit more selective, then I'm going to have to change to doing a frame switching here. If I need to adjust my detection ranges in addition to my excitation, then this is how I would have to do it. So before I go too far, let me just call these different things so that I remember which one I'm working on. All right. And from here, then what we can do is work with a couple of different combinations of the plate and everything else. So I'm going to start, let's say, with the 405. And I could do something like a short pass 505 that would actually work pretty nicely with everything, honestly. So this might be the easiest way that I could set this up here. The other thing, yeah, so we could just do something like this. For the 488s, in this case, maybe I want to use something like this short pass 550. So in this case, it's only letting through everything from here and below. My 488 isn't going to excite my DAPI, so I should be in good shape. I can do similar things with the 561 here. In this case, I could do it like this if I wanted to. So this is basically one option, to just keep on changing these different long pass filters and use a plate at the bottom. This probably would be pretty flexible. And then here, what I'm going to do instead is we should have a long pass, but we don't have a long pass like 650 or something like that with this one. So I'm actually going to do something like this here. So again, this is going to give me just this range. We don't expect any signal back here. We don't get backwards fluorescence or higher energy photons. So that should be good. And this range is nice and trim as well. This range should be nice and trim as well. Does that make sense? Now, I usually get a little bit more complicated than this. So I usually do, let's say, like a short pass 550 here for this one. And then maybe I'll work with that and I'll do like the green and the red range like so. And that way I can keep that same short pass 550 filter for the DAPI. And I can instead use a different filter here to maybe, let's say, do DAPI range plus a red or a far red or something like that. So we could do something like this. And what this allows me to do is to keep a couple of these filters the same across multiple things here. So I've got this same filter for that. And then for the red, I'm going to choose here instead, let's say like a long pass, maybe 525. And I'm going to choose that same long pass for this far red one right here. So that way these filters don't move as much. And then for the red, we're just going to use the bottom filter more. So this one's going to do a little more work in this case. So here again, with this one, I might stick with that same filter that I had, which was the green and the red. So that's going to collect just this narrow range right here. And for this one, then what I can do is I can use, I'm still going to use that same filter actually. Yeah, or we could do it like that. So there's a lot of flexibility in terms of how you work with the Airy Scan detector to build these. And so it's definitely worth kind of spending a little time playing with it. It's a bit like a puzzle box, I suppose, as you work with these two different combinations to piece things together. The range that matters is the range that's colored down here. And so, you know, even if you have something that looks like it might be getting the wrong channel, if it's not lit up, then it doesn't really matter because, again, it's the combination of these two that really dictate what you're going to end up getting in terms of emission signal in the end. All right. I think I like that first configuration better, but I wanted to kind of leave this here so that you've got a couple of different options. So let me go here and I'm just going to call this, we're going to rename it and we're just going to call it best. All right. How's everybody doing so far?
Good.
All right, good. Again, this is basically filter-based hardware setup like you would use for Airy Scan. With the confocal, we showed the option of working with the multiple detectors to get individual channels worth of information. And I guess the other type of configuration that I should really show you is the spectral imaging that we can do as well. And so for this, I'm just going to create a new one. I don't think that I left you with the spectral configuration, and honestly, I usually don't, but maybe I'll leave one behind just for fun. So I'm going to create a new configuration. We're just going to call this Zeiss Spectral. That's really it. And in this case, what I'm going to do, let me make this interface look normal. So in this case, what I'm going to do is out of the options that I have to choose here, I'm going to choose this one that's called LSM Lambda. And so for this, let me bring this out so that we can take a look at it. You can see that we can choose to add a bunch of different dyes in a different place on top here. So again, I can choose to add, I'm going to do this for the slide that I have on here, I think. So I'm going to do this for DAPI, I'm going to do this for 488, but you can basically choose all of the different floors that you're working with in your sample, just to see what those overlap curves look like. And then this is a 568-ish. All right, so this is what my emission curves look like. You can use the side detectors while you're doing spectral. Most of the time, we really just engage the central one here, and we can really pick whatever range we want to work with this. I can choose my different lasers. So in this case, I want to use my 488 and my 561. There we go. And I want to use my 405 here for the DAPI channel. Okay. So, and you can see that those beam splitters change to match the lasers that I've selected. So spectral imaging is a little bit different because we're really just going to, this is true one-track imaging. We're going to fire all of our lasers at once. We're going to collect all of our different emission signals at once. And these basically extend, even though they're overlapping, they're going to have different contributions across the entire range here. And as a result of that, what I can do is some linear unmixing to take a look at every one of these spectral bins and figure out what component is associated with DAPI or with 488 or with 561 here. And so you can see that we have different resolution ranges that I can work with as well. I could make this a lot coarser. Number one, I guess, I can change the range here if I want to. So just like before, I can impose on my spectral detector a bit if I want to, but there's really no reason to in this case, because we're doing everything in a single scan. The only reason would be to maybe reduce file size a little bit. But these tails for spectral can really help to identify the fingerprint for each one of these fluorophores, which can be quite helpful. Now, I can work with that range a little bit. I can also work with the resolution. And again, for the sake of file size, if you can get away with it, you could maybe do a coarser type of binning. In this case, each of these 32 different detector elements has a spectral range of 8.8 nanometers. We're basically binning 2 of these detectors here, or 3 or 4 of them in total. And so we're collecting less channels as a result, but we're still collecting all of the light and using it, which can be nice. We can do 8.8 naturally, which is basically the physical size of those spectral detector elements. We can also do something smaller than that. So I could instead try to go finer and tease apart signals that are even closer together if I wanted to. But when I do this, you'll notice that we go from one scan to, in this case, I think we've been running this for a long time today. In this case, we're going to end up doing 64 scans, okay? And if I wanted to do less, I could change this range. And now you see it is going to make a difference in terms of the overall number of scans that we're collecting, if we give it a second. So the reason for this is because now we're basically not relying on the spectral detector to naturally separate things out into that 8.8 nanometer bin, but we have to go back to these prisms elements that we have and these stops to basically send even narrower bands to a portion of each of those detectors. And so we now have to move something again. And so it'll take a little longer, and it basically means that we have to do this sequentially. So we have to move those between every single scan to be able to collect the entire image. So the point is, I highly recommend not going anything lower than 8.8 nanometers. You really don't need to anyway. I've been able to separate out 2 different greens and 2 different reds that are very close together, just using the standard 8.8 nanometer binning. So work with it like that. Again, we're firing all of our lasers at once. We are collecting all of our signals at once. And I've got my lasers and everything ready to go. So this is what a spectral configuration would look like. And like I said, I'll save this one here for you so that you've got it as an example. Now, let's take a look at what this is going to look like in terms of the image. And it's been a while since I've worked on this. Hopefully we haven't drifted in focus too much, but let's give it a try. Definitely have drifted in focus a little bit. All right, so if we turn off the single channel here down at the bottom, then you can actually see all of my different bins represented across the bottom. This is basically all 32. And you can see the midpoint of the wavelengths that they're working with. And the colors that are chosen here represent effectively what that emission would look like if we could actually see it by eye. And so what I can do with this is, either with single channel or with range indicator, I can basically work with my different laser powers to try to balance the emission of each of these different signals, but it's pretty good, honestly, where it is. You'll notice that I get one gain to work with. So when I change this for one of these channels, I change it for everything. And electronically, this is because this detector has 32 different anodes and one cathode. Basically, what it means is I can only apply one voltage across everything to get it to work properly. Now, what that means is that I don't have the luxury of working with separate gains for everything. So I actually do rely on my laser power more to be able to balance the emission signal between these different fluorophores. And so you can see that I can try to tune this a little bit. I don't really need to go that high for my 488s. My DAPI looks like it's pretty nice signal as well. I think the only one that I might increase a little bit is my red. And this could even be just because I am a little bit out of focus for these stress fibers on the sample because I want to get some nucleus too. So that looks like it should be about fine. And this is effectively, I mean, other than this slightly different way that you work with it and make adjustments, this is pretty much the way that we work with Spectral, very similar to what we've done with all of the other scans so far. So if I snap this image, let's take a look at that and see what it's like. Here we can do, and I need to take a better image than that, that's terrible. Let's do bidirectional, let's do a little bit of averaging. Let's do 16 bits. All right, let's try that. That should be a lot better. Terrible image, not trying it there. That's a little better. The sample also is probably about 5 years old. So BPA lasts a long time, but
expression slide.
yeah, exactly.
That was my favorite.
It could even be one of the originals. Yeah, I'm not sure. So anyway, here you can see, you know, the separation between each of these channels. I could split it, which isn't going to be too pretty. I can do a gallery view as well, which is nice in the sense that under here, in terms of appearance, I can actually show dimensions. I can see what these different wavelengths are here. So this can be kind of nice. I can still use range indicator in this view. And so I can make sure that none of these different channels are saturated. But what I really want to show you is you can see here the range of distribution of each one of these different fluorophores. So your DAPI, you can see, basically starts around here, around 425. And you can see it basically extending here. You can see that it drops here, and I'll talk about that in a minute. But it really does extend, honestly, out into these like more yellowish ones right here. This is exactly the reason why I was running into problems with some crosstalk between this and my red channel. The green, in contrast, really picks up here after the 488s or 495 or so. This channel is dark because we have that filter in place for the laser. And so we're blocking out a lot of signal by using that main beam splitter in this case. We have a little notch in our emission curve that we're used to seeing, and I'll show you what that looks like in a second. Same thing goes with the 561 here as well. And so you can see nicely basically just the distribution across all of these different fluorophores, right? I hardly have any signal out here past maybe 630 or 640, so really could have trimmed those off and not really lost much in terms of my fingerprint, but let's give it a try and see how it works. Everybody with me so far? To work with this image, this is a lot of data, right? So I'm going to move now to this unmixing tab that we have beside the image as one of these other views that we have for it. I have a number of different unmixing tools that I can work with, and you can see those here. And I can either handpick different regions, or I can use something that's called automatic component extraction. And I can separate these out using an algorithm that we have running in Zen. So if I'm going to try this, then I just need to tell it that I think I have 3 different components here. Click OK. It'll take a second to think, and it'll try to separate those out. and it probably did a pretty good job in this case. You can see the pixels that it chose for this classification. So you can see that it chose for the DAPI right here. You can see that it chose for the green right here. You can see that it chose for the red right here, okay? This is the one that I trust the most. These two, I think you're gonna end up getting a little bit of overlap here, but we can try separating it and we'll see how well it works, all right? In terms of looking at these curves, you can see that they're kind of like the emission curves that you saw in the talk earlier, except that they do have this little cutout in a couple of different places. And this is that notch dichroic, basically cutting out signal at those two different spectral bins that we collected. But that's okay, it doesn't matter, because we're gonna factor that in to the fingerprint that we just created here. And so, you know, it's a signature that's gonna be unique to this microscope, but we can use this to unmix and we're gonna see how well we do. I'm going to do auto scale. I'm going to create a residual channel so we can take a look at that. And I'm going to leave weighted unmixing alone for the moment. I'm just going to leave it at the default settings. And I'm going to click this linear unmixing button at the very bottom here. And we're going to see what we get. Sometimes automatic component extraction works very, very well. Other times it fails miserably. So let's see what we get. If we look at this, we zoom in a little bit. So let's look channel by channel. So DAPI looks very pure and actually pretty much the same thing as what we were seeing earlier. If I min-max it, you see, yep, we have like a couple of little blebs out here, but otherwise it looks very similar to what we had before. If I try to ramp up my gamma to bring out midtones, I can see that I'm not really getting any other structures any more or less than I was before. And here, this is where we're going to run into some problems. So for the green, you can see that we are getting some nuclear component to this as well. So this is not a good fingerprint for the green here, basically. And I'll show you where I saw that coming in a second. And then for the red, again, you can see that it's doing a nice job of separating out the phalloidin from the other two channels. I don't think we see either a green component or a red or a blue component in there. This residual channel is showing you basically what's left over once you finish doing this entire unmixing process. And so what you want to see, you don't want to see a lot of signal. So what we're seeing here is fine. What you want to see is just a small component of each one of these. If any one of your signals overwhelms the rest of them, it generally means that that fingerprint wasn't very good when you did the unmixing. Now, but it did a decent enough job. The green gave us problems, and that's what I want to take a look at here. So you'll notice that our green component that the automatic component extraction chose does seem to have a pretty big area under this DAPI region right here. So more than we would expect from, you know, the way that the emission curve for Alexa 488 should look like. And let me go back to this spectral viewer here. Rather than looking at, I don't want to buy anything. Rather than looking at for 546, we can take a look at 488. So this is kind of what we would expect this emission curve to look like. So not that kind of broad little DAPI hump that we were getting in this fingerprint that we see right here. And so this is kind of a warning bell, maybe that, you know, this fingerprint might need some work. So the other two I'm pretty happy with. This green one right here, I could honestly just get rid of and be perfectly happy. These other two, I think I might save them for now. So I'm going to save this to the database, and I'm going to create a folder that we're just going to call training. Like so. And we can call this ACE1, we can call this DAPI. And we can save the other one as well. We're going to call this one, let's say, it does really look like it's probably 555, but I'll still call it 568. And you can see that it pays attention to the excitation lasers that were used. It does pay attention to the dichroic as well, and the objective that you're using as well, because all of these are things that are going to impact the fingerprints that you get, and the unmixing curves. So I'm happy with both of those. Now what I'm going to do is I'm just going to see if I can't find a better green, and I'm willing to bet that I know why it chose where it did, but I'm going to give it a shot anyway. So if I go in here, what I want to do is try to find a region that has green without blue and without red. So I'm going to try, and if I take a look at this, I can turn off my green and I can see where there was hardly any red, which is kind of all of these regions right here. And I'm going to try that, but I'm willing to bet that it's going to end up getting a little bit of red as a result of that. So here, let's maybe go for this area that's right between these nuclei. I can either pick a pixel, or I can pick an area. I can create any kind of region that I want with the same kind of contours that I had for the tiling tool, for example. And you can see that this is decent. Strong peak right where we would expect it to be. Not much of a component in the DAPI channel, not much of a component here either, just a little bit of a tail bleeding off. Kind of noisy though, right? Our intensity here isn't as high. We're only looking at about 60% of the dynamic range in this case. And if I move this around a little bit, or let me just create a different curve because I'm pretty happy with that for the moment. You can see that as I look across these, that, you know, I can't really do much better than the one that I got. These aren't really much brighter. One of the things that I can do to try to clean this up a little bit would be to use a region tool instead. So this is going to collect signal over a larger area. And so the noise is going to look a lot better in this case. It's a lot smoother, this curve in the end, because we are averaging across several pixels, but there's enough dark ones there that you can see that we're really kind of taking a hit in terms of our peak. So if you have a region where there is a nice intense spot, this is a great way to go. And something like this might actually work pretty decent. But I'm going to give it a try with this other one here, even though it's noisy, and we're going to see what we get. I'm still going to do the residual channel because that'll help me out a little bit in terms of determining, you know, how successful this unmixing was. I'm still going to do auto scale, and what auto scale means is that in the unmixed image, all of these different intensities are going to fill the dynamic range. So if I'm just doing a single image, this is fine. If I want to compare different images that I've unmixed, which you can certainly do, then I wouldn't want to have auto scale on because each one of them would end up scaling differently depending on the intensity of the floor in the image. All right. The other thing that I'm going to do is I'm going to check the box now for weighted unmixing. This is a slightly more sophisticated algorithm. This one takes a little bit longer to implement, but it's especially good in situations where you have noisy images and or noisy fingerprints as a result. Okay. Couple things that we haven't talked about yet are, you'll notice that we could choose a background as well. If we did have high background, we can actually represent that as one of the channels and we can subtract it out. This is great for things like autofluorescence, for example. And then we also have things like showing the table normalized for display. This really only affects the representation here. So I either get to see a table if I want to with all of the intensity information for each, and I can normalize so that everything goes to 100%. But this is kind of misleading because it makes me think that this fingerprint is as strong as the other two. One of the things that you try to do, if possible, is to have fingerprints that are roughly equal in signal strength. If you have one that's very weak compared to the rest, especially one that's kind of sinking into the noise floor a little bit, that one is going to struggle in terms of being able to tease out your signals properly. So it's a good idea to try to have fingerprints that are roughly the same strength. And what that means is I could even pick regions that are a little bit weaker in red and weaker in blue to try to match what I'm considering my brightest green signal here if I wanted to. Now, this little hump on the green, if it's not noise, tells me that I'm probably going to get a little bit of red component in this. But let's give it a try and see what we get. Yep. All right, so taking a look at single channels here. Again, DAPI didn't have any trouble with the new green that I had selected. The red looks decent as well. Wow. Here again, even though I went completely in the middle, we're still getting some DAPI component out of this also. So there might be some background that I picked up accidentally, but with the right fingerprint, we should be able to tease it out. These samples over time too basically leak a little DAPI. It's not exactly highly bound to the DNA, so I'm not surprised maybe if it is kind of leaking out here a little bit. And you know, this is, and let's take a look at the residual channel as well, just to see, again, a nice blend of everything. So that looks good. This is probably a good segue to talk about likely one of the most important things when you are considering doing spectral imaging and doing linear unmixing, which is to say that the best type of samples to pull these fingerprints from is to prepare single positives with the first run that you do, basically. So you can see, if we go back to the original image here, that there is a lot of spatial overlap between all of these signals, right? The nuclei have microtubules surrounding them. They have actin underneath them. And so I'm really struggling to pick out a clean pixel that I can use for that. Likewise for the green is either, these microtubules are either over the DAPI or they're over the actin. And there's not really much that I can do about that. So if you are lucky, when you're setting up a multiplex panel like this, then you can choose fluorophores, even if they're spectrally overlapping, you can choose fluorophores that are spatially separated. And so if you design the panel thoughtfully, then a lot of times you can get away with just doing a single label with everything and teasing apart signals that are spatially separated. If you don't have that luxury, and if there's always regions of co-localization between a couple of different fluorophores, you just can't get fingerprints without doing single positives. So in this case, you know, a phalloidin only, a microtubule only, a DAPI only would be the perfect control to get these fingerprints. So really, really important to do that. Another thing to mention, I guess, sort of going back to the topic of choosing different fluorophores that have optimal excitation and where you can collect a detection range that is suitable for the emission to collect as many photons as possible. That is absolutely true for all kinds of imaging, no matter what you're doing in spectral, and that is going to give you the maximum signal, the least amount of hassle and headache. In spectral imaging, sometimes you end up tuning and tweaking that a little bit as well. So if you know that you're working, so I used to do a lot of brain imaging, and we did GFAP for astrocytes, which is blazing signal no matter what you do, because it is so abundant. The antigen, the epitope there is just everywhere. Even if you back off on dilutions, you end up getting a ton of different signal, which can be of value, because what you can do is you can put it, for example, on a fluorophore or on a laser line on a channel where basically you don't have optimal excitation. And again, we're stuck with a single gain setting. So it's not like we can really adjust that to balance between the different fluorophores, but you can make some of your fluorophores off peak in terms of excitation, which is going to mean that those peaks in the fingerprints are going to be reduced or on a scale that's similar to the rest of these as well. And that way you can leave and reserve the optimal spectral slots for your weaker signals or your less abundant signals to make sure that they have the best chance possible to shine in like a sea of other fluorophores, basically. So if you balance things right, both between spatial separation, between spectrally separating fluorophores or targets that you think are going to co-localize. If they are going to co-localize, you probably want them to be spectrally as far apart as you possibly can, so that you have confidence that you are really getting co-localization in those cases. And then finally, in terms of working with the excitations, to make sure that you can get a good balance of signal across all of your fluors and across the entire spectrum. How is everybody doing? Does that make sense? Sort of. It's the kind of thing you really need to play with and practice. And it's the kind of thing where good design before you even walk up to the microscope or before you even start labeling your samples can save you a ton of time. Spectral imaging really is made or broken on the fingerprints that you're able to generate. So if you have good fingerprints, you can do amazing things to separate out fluors and autofluorescence that are very overlapping spectrally. And if you have bad fingerprints, then it just looks like a bowl of spaghetti. It just looks like it's all over the place. If anybody wants any math on any of what we've talked about here as well, I do believe I tried to leave behind for you an unmixing guide as well. Do I have that here? Let me check the other folder. I will make sure that you have it anyway. You should have it. Ah, there we go. Okay, yeah, there's a couple. So linear unmixing or linear unmixing for dummies. Can't quite remember which one is going to have all of these different pictures for you. Blah, blah, blah. This is the Zen stuff, how you set it all up. What I'm looking for is, and it talks about proper controls and everything else. What I'm really looking for is something that kind of shows the, this one might be the one. I just want to see something that kind of shows you the math and the breakdown and stuff like that. Yeah. Yeah, not the best. All right. I can go here, at least I know that. Just because we have a little more time, if nobody has questions, I can at least try to show you a little bit more of the theory behind this, if anyone is interested. All right. So in addition to the knowledge base that I mentioned, it's worth mentioning that just like many others, we do have a online campus that we've had around for a while. So lots of different topics, articles that you can go to, and guides basically for some of what we've been talking about here as well. I'm going to take a second to do this introduction. There's also the practical considerations is very good as well. And so just to give you an example of what some of this can look like. So basically, you know, this is the way that we talked about doing things in the first place, with very discrete emission filters and excitation filters. Again, with linear unmixing, we're just basically collecting all of our signals across an entire range of spectra in what we call a lambda stack. So it's kind of like an extra spectral dimension of information to our image. And we really are just collecting all of the signal and basically binning it. This is what we saw in the image, where we're basically breaking down the intensity of each of these components at each of these spectral bins. And you can see that there's a shift between all of them, and that's what we use to basically do the separation. This one at the bottom here, that's what we're using. And let's see, I think we have a little bit of math as well. So basically the sum of the signal at every single pixel is basically made up of the each of the different components, let's say A, B, and C, or blue, green, and red, along with the residual as well. And so it's really as simple as that. It's a sum total of the intensity, but where the least squares regression and the linear unmixing comes in is that we're basically looking across all of the different spectra at every single pixel to figure out what component is best represented by a certain concentration of blue, green, or red. And once we do that across everything, that's where we're able to basically come up with that separation in a nutshell. I think that's as far as I want to go, unless someone is curious. Yeah, I'd be happy to get into it a little more detail, but I guess one thing to show you quickly, autofluorescence, like I said, great way to remove it. So if you have background fluorescence, if you're working with brain samples where you have lipofuscin or yolk proteins in your embryos or things like that, it's the perfect tool to be able to unmix those. And one of the things that we take advantage of, the thing about autofluorescence, I'll just keep on talking, I'm sorry, just for 2 more minutes. One of the things that usually we hate about autofluorescence is that it's so broadly emitting. And so it creeps into our channels. We can try to move away from it, but somehow it always finds a way to get in there. And that's an advantage when we're doing linear unmixing because it is much more broadly emitting than all of our tightly chemistryed and controlled fluorophores that we're tending to work with these days, which have very tight emissions because we know we want to pack them together. This broadly emitting autofluorescence is very easy to pick out of that and to separate as a result. Okay. I think if there's no questions, this might be a good place to stop. Just to kind of recap everything that we've covered so far. We did the hardware, we did a basic introduction to kind of what the system can do in the morning. We did some hardware overview, and I believe that we covered really everything in terms of hardware. We did an introduction to Zen, where we basically took it from the different tabs and tools and buttons through the locate tab to the acquisition. I do need to spend a little bit more time with you on the camera, but I think I'm going to leave that until tomorrow. I did get it working at least, so that's good. And then we did some confocal imaging, working through loading a configuration, spent a lot of time in the afternoon on how that image setup really works and impacts your image quality, and working with the balance between lasers and PMT, and also working to optimize the image using the frame size, the averaging, the dwell time, and so forth. So after that, we did then in the afternoon, a big breakdown on fluorescence, why we use it, why it's helpful, and why working with filters because of the Stokes Shift is really helpful. And we talked about different ways to configure that, both for wide field systems, also for either confocal mode or Airy Scan or spectral imaging on the 980. So that's really a pretty good broad coverage of all of the hardware elements of the system. And so tomorrow what we're going to do is we're going to dive into the software a little bit more to discuss some of the multidimensional that I didn't talk about today, like tiles, positions, and focus strategies. And then we'll jump right into Airy Scan and multiplexing and show how that looks compared to the confocal images that we can collect. All right.
Great.
Does anybody, I guess an open question while everybody is here, because I think that in the afternoon, we have a little time squirreled away for demo time. And so, what's that? Oh.
Okay.
Yeah, I think so. So if anyone has a sample that they want to try, I guess maybe just let us know. And otherwise, I'm guessing you have some samples we can try working with maybe.
I have a couple things, but
Okay.
if anybody has anything that they want to bring by, feel free to drop a slide by.
Yeah.
I thought it was a great opportunity, and I tried to convince my lab to do it, but they couldn't come up with any samples.
All right, well, we'll see what we can come up with.
Yep. All right.
First quality, but
Thank you, everyone, for your attention. I know it's been a long day. I know we covered a lot of material, but hopefully it's been helpful as an introduction to the 980, and hopefully everyone has the energy to be here tomorrow, because that's when we do all the exciting stuff. All right. Thanks, everyone. Talk to you tomorrow.
Thank you so much.